Okay, part 2, where we now actually take into account the fact that this pulley on our Atwood machine is going to be massive, which in reality it always is. So we're going to have a similar sort of setup where we have a block M1, a block M2. We're still going to assume that M2 is greater than N1, and so this system should still accelerate in the same way in which M1 goes up, M2 goes down, but now we're going to have to take into account the motion of this pulley. So we're going to treat this pulley as a solid disc or a solid cylinder that's pivoted about the middle. It's got a mass, capital M, and a radius, big R. And now, in order for this to have a net torque, in order for it to undergo an angular acceleration, we have to have different tensions on either side. In other words, tension is going to act as if it were pulling downward on each of these sides. That's what tension does, is tension pulls on things. So in the same sense that each of these tensions are pulling up on their respective blocks, it's pulling down on either side of the pulley. And in order for this to have a net torque, it's going to be the case that T2 is not going to be equal to T1. In fact, if this accelerates this way, by tension T2 has to be greater than T1. So, in addition to then having a force problem where we're going to analyze the forces acting on these blocks like we saw in the previous video, we're also going to have a torque problem looking at the motion of this disc. So, we're still assuming that we have this massless rope that's not going to change its length, and so we're still going to have these acceleration constraints such that our acceleration A1 is going to be the negative of acceleration A2. In other words, this block is going to move up, this block is going to move down, but now we have to take into account that this disk is also going to move. And in fact, again, if I look at it this way, of how I've defined it, it's going to undergo a clockwise rotation, and it's going to have some angular acceleration alpha. And so that becomes, again, that's the analog of the acceleration here when we look at our pulley. Now, that is going to become another unknown, so our tensions are going to be unknown, our two accelerations are unknown, and then our angular acceleration is also an unknown. We actually have 5 unknown quantities here. So let's just take a look at what's happening on this rotating pulley. Let me redraw it over here. So, the important thing is, in the same way if we said that this rope is inextendable, we're also going to say that the rope is going to move without slipping. In other words, as this rope moves down, this is going to rotate in such a way that the rope along the edge here is going to move at exactly the same rate. In other words, the rate at which the pulley is moving is going to be the same at the same rate at which the rope is moving. Because if that were not the case, then it would be slipping. But that means that if I look at the acceleration of a point on the rim here, as far as the pulley is concerned, that is a tangential acceleration, and its magnitude is just going to be alpha times r, but that also, since it's moving without slipping, must be the same as the acceleration on the rope. So now we're going to have a constraint because the rope is moving along here. This is similar to the rolling constraint we had when we looked at wheels moving on the ground, and that is just the fact that my angular acceleration, alpha times r, its magnitude has to be the same as both our A1 up here and our A2 down here. So magnitude of alpha r equals the magnitude of A1 is equal to the magnitude of A2. That becomes my constraint. Again, this constraint coming from matching the acceleration of the rope to the tangential acceleration of the point on the rim. Notice I wrote everything there as magnitudes because we have signs we need to take into account. Got to make sure that we get our positive and negatives. As we saw before, if A1 is positive, A2 is negative. And in our convention, if we have an angular acceleration that's moving in the clockwise direction, this means that our alpha is also going to be negative, because we said moving clockwise is negative. This means if A1 is positive, A2 is negative, then alpha is negative. This means that alpha and A2 have the same sign. So we have a constraint overall that a1 is equal to the negative of a2 is equal to the negative of alpha times r. So we have, this is in fact two equations that give us our constraint equations when we're looking at the motion of this object. So we're going to work this again as a force problem, since in the end you're only interested in finding the acceleration. The only difference now is that our acceleration is going to end up not just being a function of m1 and m2, but also this mass here. So when we still have to do the force problem on these blocks. Again, we saw this from the previous video. We have m1g going down that way. We have m2g going down this way. So it's the same equations as before. Sum of forces in the y direction. Not exactly the same, because now that becomes T1 rather than just T, minus m1g is equal to m1a1. Again, tension, weight, giving rise to the acceleration. Block number 2, we have sum of forces in the y. T2 minus m2g is equal to m2a2. So we'll leave these here for now, because notice I have two equations, but then I have four unknowns. I have T1, T2, A1, A2, again, assuming we know the masses. So now we've done the forces that are acting on these blocks. Now we have to come over here and look at the torques that are acting on this disk. If this disk is undergoing an angular acceleration, then there must be a net torque on it. And as we stated way up here, if I look at this object here, again, we're pivoting it at the center, so that becomes our pivot point. The tension is acting as if it were along this edge here. So we have a tension T2. Notice that's going to be at a distance r, and it's going to be exactly perpendicular based upon where it's coming off of the pulley. So the nice thing here is that I don't have to worry about angles when I'm computing these torques. Same thing on the other side. That's a distance r. This is going to be a tension T1. And that's it. Those are the only two forces that are acting on this that are going to exert torque. Notice that because I'm pivoting it about its center, even though it does have a weight, I have a capital mg that's acting at the pivot point, and so will therefore exert no torque. Then I have some other force, like a normal force, that must be holding up the block. Let me sketch those in really quickly. Right, I would have a capital mg acting this way. I would have some sort of normal force pulling up there, but since both of those are acting at the pivot point, we don't have to include them when we're writing down torque. It's important to know that they're still there. We said that this was a solid disk, so we can look up in that table that this is going to have a moment of inertia that's equal to 1/2 times capital M times r squared. And so, in the same way that when we sum up forces, it's equal to mass times acceleration, for my torque equation, I'm going to sum up all of the torques on this object, and it's going to be equal to I times alpha. So this is effectively our free body diagram, and then we have sum of torques is equal to I times alpha. So our torques, as we've stated here, are coming from these two tensions. Our tension T1, again, acting at a right angle, is tending to make it rotate counterclockwise, so that's going to give a positive torque. T2 is tending to make it rotate clockwise, so that overall is going to give a negative torque, and the value of the torque is just going to be this distance times this force here. So my sum of torques, I'm going to have R times T1, again, that's positive. I have minus R times T2, because that's going in the other direction, minus R times T2, and that must be equal to I times alpha. Well, I is equal to 1/2 mr squared multiplied by alpha. Okay. Notice immediately I can factor out an R. So I have T1 minus T2 is equal to 1/2 mr squared alpha. And so in fact we can cancel one factor of r. We can just divide by r on both sides. So this would give me T1 minus T2 is equal to 1/2 mr alpha. But notice that in order to connect this with the other expressions up here, I'm eventually going to have to use this acceleration constraint. And this acceleration constraint said that alpha r has the same magnitude as a1 and a2. So in fact, alpha times r here is in fact just equal to a2, which means I can even now rewrite this, t1 minus t2 is equal to 1/2 times big M times a2. In other words, I have an expression that looks like a Newton's second law problem. I have no references to any distances or any moments of inertia. It looks like I have these two tensions that are exerting a force on a mass. Again, the pulley itself, its center of mass isn't actually moving, but effectively the entire radius is going to cancel out. And that's really the important thing, is that for this problem, it's not going to depend what the radius of this pulley is. It will depend upon the mass, and the mass is actually what you're going to be trying to find in this week's online video. Now, notice that work still isn't completely done, but I'm gonna sort of let you take it from here. But just summarizing where our equations came from. Again, our torque equation was this. We had our force equations, and so those are up here. And then we already used one of our acceleration constraints. We can use the other constraint that a1 is equal to the negative of a2. And so bringing all of these together, so our two force equations, our acceleration constraint, and our torque equation here, we can solve for example, our acceleration a1 in terms of each of these masses, m1, m2, and capital M. And we'll get a similar looking expression to what we had before. And we proceed like we would normally, like sort of what we did before. I take each of these and I solve for the tension. I have T1 is equal to something, T2 is equal to something, and then I stuff them into this equation. And then I eliminate A2 by having an A1, and then I do a whole bunch of algebra. Or rather, you're going to do a whole bunch of algebra to eventually get it here. So in the end, you're going to have this, and then in the lab, you're going to measure this A1 using video capture, and then given the masses of M2, you're then going to use the results of this expression, essentially are going to turn around and solve for it to measure the mass of this pulley. So that's what's really happening in this lab. You're going to measure an acceleration of these blocks, and then you're going to determine the mass of the pulley from working through a problem like this. So I think this is where I'm going to end up. If you have any questions, as always, send me a message and I'll answer it. Bye.